Welcome to Lasea class. I am your teacher, Jan Lasea. Today we are going to learn handwriting digit recognition using ANN or Artificial Neural Network. The human brain is made up of a complex network of neurons. Our brain has 86 billion neurons that are interconnected to each other. Neurons, also known as nerve cells, send and receive signals in our brain. Neurons use electrical impulses and chemical signals to transmit information between different areas of our brain and between the brain and the rest of the nervous system. The artificial neural network simulates the neurons in our brain to learn to recognize or classify handwritten digits from 0 to 9. Artificial neural networks, usually simply called neural networks, or more simply yet, neural nets, are computing systems inspired by the biological neural networks that constitute animal brains. An artificial neural network is an attempt to simulate the network of neurons that make up a human brain so that the computer will be able to learn things and make decisions in a human-like manner. Artificial neural networks are created by programming regular computers to behave as though they are interconnected brain cells. An artificial neural network is based on a collection of connected units or nodes called artificial neurons, which loosely model the neurons in a biological brain. Each connection, like the synapses in a biological brain, can transmit a signal to other neurons. An artificial neuron receives signals, then processes them, and can signal neurons connected to it. Artificial neural network is a mathematical function that maps a given input to the desired output. To understand what that means, let's take a look at a single-layer neural network known as perceptron. The perceptron is a mathematical function that takes in a set of inputs, performs some mathematical computation, and outputs the result of the computation. The perceptron uses the linear function y hat is equal to the summation of the product w sub I, which is the weights or the slope, and x sub I, which are the inputs, to be added to the bias b or the y-intercept. There are several ways artificial neural networks can be deployed, including to classify information, predict outcomes, and cluster data. As the networks process and learn from data, they can classify a given data set into a predefined class. It can be trained to predict outputs that are expected from a given input and can identify a special feature of data to then classify the data by that special feature. Google uses a 30-layered neural network to power Google Photos, as well as to power its What's Next recommendations for YouTube videos. Facebook uses artificial neural networks for its deep face algorithm, which can recognize specific faces with 97% accuracy. It's also an artificial neural network that powers Skype's ability to do translations in real time. The components that made up a neural network are an input layer, name X, an arbitrary amount of hidden layers, an output layer, y hat or variable z, a set of weights and biases between each layer w and b respectively, a choice of an activation function for each layer alpha. Some examples of activation function are sigmoid or logistic, rectified linear unit, ReLU, softmax, and hyperbolic tangent, to name but a few. An activation function is a function that is added into an artificial neural network in order to help the network learn complex patterns in the data. Here is an example of a two-layer neural network. Note that the input layer is typically excluded when counting the number of layers in a neural network. A two-layer neural network consists of a input layer, a one hidden layer, and an output layer. So if we count how many layers, all in all, the hidden layer is counted 1 and the output layer is counted 2, and the input layer is not counted. The output at each node called its activation or node value. Neural networks with many hidden layers, such as 10 hidden layers, 100 hidden layers, 1000 hidden layers, are considered deep networks, and their application is called deep learning. Training the neural network is the process of fitting a model to a data set. It is the process of fine-tuning the weights and biases from the input data. Each iteration of the training process consists of the following steps: calculating the predicted output y hat or z, known as feed forward; updating the weights and biases, known as back propagation. Neural networks are typically created with all parameters initialized as small random values between 0 and 1 from a Gaussian or normal uniform. Once an observation, or more often a set of number of observations called a batch, is fed through the network, the outputted value is compared with the observation's true value using a loss function. This is called forward propagation. The cost function and loss function and error function refer to the same context. For example, the training process that uses backpropagation to minimize the error between the actual and predicted outcome. We calculate the cost function as the average of all loss function values, whereas we calculate the loss function for each sample output compared to its actual value. Our goal in training the neural network is to find the best set of weights and biases that minimizes the loss function and increases the accuracy of prediction. There are many loss functions to choose from in performing the backpropagation to minimize the error between correct and wrong prediction, such as mean squared error, and sum of square errors, to name but a few. Next, an algorithm goes backward through the network, identifying how much each parameter contributed to the error between the predicted and true values, a process called backpropagation. At each parameter, the optimization algorithm determines how much each weight should be adjusted to improve the output. Once we measure the error of our prediction, the loss, we need to find a way to propagate the error back and to update our weights and biases. In order to know the appropriate amount to adjust the weights and biases by, we need to know the derivative of the loss function with respect to the weights and biases. In calculus, the derivative of a function is simply the slope of the function. If we have the derivative, we can simply update the weights and biases by increasing or reducing with it. This optimization method is known as gradient descent. The word gradient is called slope. We learn from algebra that if the slope of the linear function is negative, then it means the slope is decreasing. On the other hand, if the slope is positive, then it means the slope is increasing. In calculus, by finding the first derivative of a function, we can compute the local minimum if the derivative exists. The local minimum suggests that the point is at the lowest part of the graph of the function. This local minimum would suggest that we found the appropriate gradient as we descend to the graph of the function. If the derivative or gradient or slope is negative, then increase the value of the weight. Else, if the derivative or gradient or slope is positive, then decrease the value of the weight. The MNIST database, or Modified National Institute of Standards and Technology database, is a large database of handwritten digits that is commonly used for training various image processing systems. The database is also widely used for training and testing in the field of machine learning. The NIST training datasets was taken from American Census Bureau employees, while the testing dataset was taken from American high school students. Furthermore, the black and white images from NIST were normalized to fit into a 28 by 28 pixel bounding box and anti-alias, which introduced grayscale labels. Each handwritten digit image has a resolution of 28 width and 28 height resolution. The pixel 0 is treated as white, but in reality it is black, while the pixels from 1 to 225 is treated as black, but in reality it is white. As of this date, the MNIST database contains 60,000 training handwritten images and 10,000 testing handwritten images. Half of the training set and half of the test set were taken from NIST training data set, while the other half of the training set and the other half of the test set were taken from NIST testing data set. You can download the CSV format at this following URL address at the Kaggle website. The following codes written in Python will convert a normal image having a white as background and black as forecolor into MNIST image. After reading an image file, the line img underscore data is equal to 255 minus img underscore array dot reshape 784 will invert pixel 0 to white as foreground color and pixels from 1 to 225 to black as background color, and then scale the pixel data from 0 to 1 and displays the image on the monitor screen. Let us apply artificial neural network to recognize our predict or predict handwritten digit. The training data are examples of true truth values used to teach the neural network model. Also, it is used to adjust the weights of the neural network. Our training data is the MNIST database that contains 60,000 handwriting records stored in the file MNIST underscore train underscore 60k.csv. I removed the first row containing the header. The test data is used as a final test to gauge how accurately the neural network has been trained. Our test data is the MNIST database that contains 10,000 handwriting records stored in the file MNIST underscore test underscore 10k.csv. I removed the first row containing the header. I made 4 test images with resolution of 28 by 28 with white background and black foreground using a paint software for further testing. Example code number 1. I got the example Python code of Rashid while reading his book entitled Make Your Own Neural Network. The code of Rashid has 2-layer neural network. The input layer consists of 784 nodes or neurons because 28 multiplied by 28 is a product of 784 pixels. It has one hidden layer consists of 200 nodes or neurons. The output layer consists of 10 nodes or neurons because there are 10 digits from 0 to 9 to classify or predict. This is the source code of Rashid that I got by reading his book entitled Make Your Own Neural Network. It was written in Python programming language. At line 50, the code uses the following libraries, namely NumPy, SciPy, Matplotlib, Image.io, OS, and Time. At line number 62, the global variables declared are hyperparameters, namely input underscore nodes initialized to 784, hidden underscore nodes initialized to 200, output underscore nodes initialized to 10, and learning underscore rate initialized to 0.1. At line number 70, the class-defined name neural network encapsulates the training and prediction of the model. At line 72, the constructor init accepts values and stores to the class properties, namely I nodes, H nodes, and O nodes. At line number 82, the property name WIH or the 200 input weights of the hidden layer are initialized using normal distribution. At line number 83, the property name WHO or the 10 output weights of the output layer are initialized using normal distribution. At line number 89, the neural network model uses the sigmoid or logistic function, as activation function. At line number 92, the method definition name train accepts the 784 pixels and validation data containing the 784 values of 0.99 as target values. At line number 98, it will calculate the signals into the hidden layer. At line number 100, it will calculate the signals emerging from the hidden layer. At line number 103, it calculates signals into final output layer. At line 105, it calculates the signals emerging from final output layer. At line 108, the output layer error, it will compute the output layer error by finding the difference between the target and the actual. At line number 110, the hidden layer error is the output errors split by weights recombined at the hidden nodes. At line 113, it updates the weights for the links between the hidden and output layers. At line 116, it updates the weights for the links between the input and hidden layers. At line 119, the method definition name query accepts the 784 pixels and predicts the digit label. At line 124, it calculates signals into hidden layer. At line 126, it calculates the signals emerging from the hidden layer. At line 129, it calculates the signals into final output layer. At line 131, it calculates the signals emerging from final output layer. At line 135, the method definition name prediction is not part of the class neural network. It accepts the image file path name and the instantiated object of class neural network. It will predict or classify the image into a digit. At line 167, the object name n is instantiated using the class neural network, and we pass values of input nodes, hidden nodes, output nodes, and the learning rate. At line 171, it loads the file MNIST _train _60k.csv containing 60,000 handwritten records for training the neural network model. At line 178, the value of the epoch is set to 10. At line 182, the nested loop trains the neural network model. At line 204, it loads the file MNIST _test _10k.csv containing 10,000 handwritten records for testing the neural network model. At line 215, this loop predicts the 10,000 handwritten records and tallies the correct predictions of the neural network model. At line 239, it then displays the score and performance. Beginning at line 245, the neural network model is tested on the 4 sample images and displays the result. Ladies and gentlemen, let us run and test. The program took 29 minutes 46 seconds to train the neural network model. And here are the results. The score is 9,753 correct predictions out of 10,000. And the performance is 97.53%. The displayed number to be predicted is 2. And the neural network model predicts that it is 2, which is correct. Next, the displayed number to be predicted is 3. And the neural network model predicts that it is 3, which is correct. Next, the displayed number to be predicted is 5. The neural network model predicts that it is 5, which is correct. Next, the displayed number to be predicted is 8. The neural network model predicts that it is 8, which is correct. And it is very good. Example code number 2. I got the example Python code of Samson Zhang at the Kaggle website. This site is one of the best places to learn artificial neural networks and machine learning. And it was written from scratch, with no usage of TensorFlow and PyTorch libraries. I modified and improved the code of Samson Zhang to predict digits from test data and images, instead from the trained data sets. The code of Zhang has two-layer neural network. The input layer consists of 784 nodes or neurons because 28 multiplied by 28 has a product of 784 pixels. It has one hidden layer consists of 10 nodes or neurons. The output layer consists of 10 nodes or neurons because there are 10 digits from 0 to 9 to classify or predict. This is the source code of Samson Zhang that I got at the Kaggle website. I modified and improved the code of Samson Zhang to predict digits from test data and images instead from the trained data sets. The code was written in Python programming language. Beginning at line number 51, the code uses the following libraries, namely Image.io, NumPy, Pandas, Matplotlib, and Time. At line number 58, it loads the file MNIST_train_60k.csv containing 60,000 handwritten records for training the neural network model. At line number 60, the global variable name data contains the 60,000 handwritten records and converted into NumPy array. At line number 65, the data is shuffled because the order of the data can cause the network to become biased during the training of the neural network model. At line number 69, the global variable name y_train is the validation data. It contains the key answers or digit labels. It is used to minimize a problem known as overfitting. At line number 70, the global variable name x underscore train is the training data. At line number 72, the contents of the variable x underscore train are scaled from 0 to 1. It is important to scale the data in order to ensure that the backpropagation algorithm works as intended. After applying the scale, it shrinks the magnitude of the variables, transforming them to a scale that is more proportional. At line number 79, the method definition name init underscore params initialize the variable w1 as weights for the hidden layer, variable b1 as biases for the hidden layer, variable w2 as weights for the output layer, and the variable b2 as biases for the output layer. At line number 87, the method definition name ReLU or rectified linear unit accepts the gradient or slope of the hidden layer, and it calculates the rectified linear unit function. The neural network model uses the ReLU as an activation function during the forward propagation. At line number 91, the method definition name softmax accepts the gradient or slope of the output layer, and it calculates the softmax function. The neural network model uses the softmax as an activation function during the forward propagation. At line number 96, the method definition name forward underscore prop is the forward propagation. It calculates the gradient or slope for the hidden layer. It applies the rectified linear unit or ReLU activation function on that gradient or slope. It calculates also the gradient or slope for the output layer, and it applies the softmax activation function on that gradient or slope. At line 104, the method definition name ReLU underscore derive determines the sign of the gradient or slope z. At line 110, the method definition name 1 underscore hat is a 1 hat encoding for the y underscore train validation data that create new 10 classifications that take on values of 0 and 1 to represent the original 10 classifications of digit values. The line at 117, the method definition name backward underscore prop is the backward propagation that calculates the derivative to chain of partial derivatives during the gradient descent. The line at 128, the method definition name update underscore params adjusts the weights and biases after the backward propagation during the gradient descent. At line 136, the method definition name get underscore predictions returns the predicted digit from the neural network model. At line 141, the method definition name get underscore accuracy computes the average of correct predictions of the neural network model by counting the correct predicted digit and divides it to the total items. The line at 147, the method definition name gradient underscore descent is the optimization method that finds the best set of weights and biases that minimizes the loss and increases the accuracy of prediction. It trains the neural network model by performing iterations of forward propagation backward propagation, and adjustments of weights and biases. At line 162, the variable alpha is set to 0.10 value. This hyperparameter is the learning rate. At line 163, the variable iterations is set to 1500 value. It is a hyperparameter that sets the number of repetitions for improving the prediction bit by bit during the training of the neural network model. At line 166, it calls the method name gradient descent to train the neural network model. At line 174, the method definition name make underscore predictions. The neural network model predicts the digit from the 784 pixels data. At line 181, the method definition name prediction opens a 28 by 28 image file and performs the digit prediction using the final computed weights and biases. At line number 200, it loads the file MNIST underscore test underscore 10k.csv containing 10,000 handwritten records for testing the neural network model. At line 222, this loop predicts the 10,000 handwritten records and tallies the correct prediction of the neural network model. At line 235, it then displays the score and performance. Beginning at line 241, the neural network model is tested on the 4 sample images and displays the results. Ladies and gentlemen, let us run and test. The program took 16 minutes and 2 seconds to train the neural network model. And here are the results. The score is 8,970 correct predictions out of 10,000. And the performance is 89.70%. The displayed number to be predicted is 2. And the neural network model predicts that it is 2, which is correct. Next, the displayed number to be predicted is 3. The neural network model predicts that it is 3, which is correct. Next, the displayed number to be predicted is 5. The neural network model predicts that it is 3, which is wrong. The displayed number to be predicted is 8. The neural network model predicts that it is 8, which is correct. And the results are good, very good. These are the results that I got after running and conducting the 10,000 handwritten test and 4 sample images test. Under the 10K test, the code of Rashid got a score of 9,756 correct predictions out of 10,000, and the performance is 97.56%, and the test error rate is 2.44%. On the other hand, the code of Zhang got a score of 8,907 correct predictions out of 10,000, and the performance is 89.07%, and test error rate is 10.93%. We cannot conclude which is the better code. However, we can improve or increase the performance and lower the test error rate of both the codes of Rashid and Zhang by increasing the amount of iteration, epoch, and trained data. Under the 4 sample images test, the code of Rashid got a score of 3 correct predictions out of 4, and the performance is 75%, and the test error rate is 25%. On the other hand, the code of Zhang got a score of 3 correct predictions out of 4, and the performance is also 75%, and the test error rate is 25%. According to Jason Brownlee, neural network algorithms are stochastic or random. This means that they will make different predictions when the same model configuration is trained on the same training data. The weights and biases are initialized randomly during the start of the program. And every time that we train the data and determine the prediction, it will be different. It will be different all the time. According to the MNIST database website, the Committee of 35 Convolution Network 1-20-P-40-150-10 elastic distortions with preprocessing with normalization has a test error rate of 0.23%, which is very close to 0, which is very accurate, highly accurate as of this date. That ends our topic for today. I hope you are inspired in my class. Thank you for watching. God bless us.